Okay, so we are doing medium buffer. I lost my pen. Oh, there it is. Okay. Um, Medium buffer problem, and in fact, this problem actually isn't much different than one you've already done. It actually isn't different than one you've already done. When you first look at this problem, it should not look like a buffer problem to you. So let's talk about it. So we're calculating the pH, and we're taking ammonia, so that's one of my major species. Whoa. Okay, let's try that again. Ammonia, NH3, weak base, right? Okay, and HCl, strong acid. Okay, so this should look like a neutralization reaction. Base and acid, okay, will give you salt and water. It should not look like a buffer problem at first glance to you. So, I do see that the two solutions are mixed, so I'm going to go ahead and do the dilution. So I'll do it for ammonia, and then I'll do it for hydrochloric acid. Ammonia's molarity is 0.4. I have 50 milliliters of it. New molarity after they're mixed, and it looks like the final volume 50 and 50, so 100. Okay, so the ammonia, if you calculate that out, comes out to be 0.2 molar ammonia. Okay, and then you dilute the acid. The acid is 0.2 molar. Jeez. Excuse me. All right, back to our regular scheduled program of acids and bases. So I think I was ending at this being 50 milliliters. New molarity and final volume again is 100. And after you do that, you end up with 0.1 molar HCl. Okay, now this is an actual reaction. This is a weak base reacting with a strong acid. Okay, so you have weak base, which doesn't ionize. You have strong acid, which completely ionizes. Okay, is going to make NH4 plus. Now, here's what's tricky. So this would be ammonia. This would be HCl, right? This would be ammonium chloride. That's your salt, which all I care about is ammonium. And then you go, well, where's the water? Well, you don't see it here when you do it this way. So I'm going to just show you. You can rewrite this strong acid as H3O plus so that you can see the salt. This accepts a hydrogen, this loses a hydrogen. In this instance, you can see the water, okay? Again, these two are the same. Why is it a one-way arrow? Because we're doing neutralization. This isn't just a weak acid by itself or a weak base by itself. It is an actual chemical reaction, okay? So now we're going to start an ICE chart, ICE. Now we have amounts of both reactants. We have ammonia, it's 0.2 molar. We have strong acid, it's 0.10 molar. Now, we don't have any salt in there. There's no other source of salt, and water's a liquid, so we don't care about it. So this is a limiting reactant problem. We're going to lose all of the strong acid because they're reacting in a 1-to-1 ratio, and we're going to lose the same amount of base, and we're going to gain that amount of salt. Okay, so at the end, we don't have any acid. It ran out. We have 0.1 molar of the base and 0.1 molar of its conjugate. So this has turned into a buffer problem. I have weak substance and its conjugate present. So again, there are two ways to go about this. You can solve using the Kb expression. Kb equals products over reactants raised to their coefficients. Okay? I'm going to just go ahead and solve using Henderson-Hasselbalch. I recognize this as a buffer, all right? A weak substance with its conjugate. So I'm going to do it as POH because this is a base equals PKB plus the log, weak base on the bottom, conjugate on top. And then I'm just going to plug and chug into there. POH equals PKB, which means opposite the log of KB. Opposite the log of 1.75 times 10 to the negative fifth plus the log of 0.1 of the base, right there. I'm going to change color so we know we're talking about the same or different parts, even though they're the same number. This guy is the conjugate that goes on top. Now, the log of 0.1 divided by 0.1 is 1. So the log of 1 is 0. So POH equals PKB. So POH equals 4.76. So the pH equals 9.24. Now, during a titration, this is a special point, okay? This is called the half equivalence volume, okay? It's called the half equivalence point because you have half of the equivalence volume. It always works out like this, okay? Half equivalence point. And because we're starting off with a base, so this is where in an acid pH equals pKa. If it's a base, POH equals PKB. Okay, now look at something interesting. Okay, I want to go back up here to the top and change my color. Okay, you have 50 milliliters of 0.4 molar base. Okay, you have the same exact amount of acid, HCl. Okay, same exact amount of the acid. How do I erase? Let me see. Let me go back real quick. The acid, sorry, is 0.2 molar. So without doing any math, okay, the base is twice the concentration of the acid. So if I have 50 milliliters of base and it's more concentrated, I'm going to need more acid to help neutralize it. Specifically, the equivalence volume should be 100 milliliters of the acid to completely and perfectly neutralize the 50 milliliters of the base. Again, the base is double the concentration of the acid, and you have 50 milliliters of it, so we're going to need double the volume of the acid to neutralize that highly concentrated base. So this right here is equivalence, right? It will take 100 milliliters of acid to be the equivalence point. Well, look how much is given in this problem. 50 milliliters of the acid. So look at 50 is half of 100. This is your half equivalence point of a titration. Again, it's called buffer medium, but it doesn't start out as a buffer. It's an acid and a base neutralization reaction that produces a buffer, okay? So that is how you calculate this buffer medium problem.